There are two big theories in physics. One is general theory of relativity and the other is quantum mechanics, which describes the universe we perceive. General relativity describes the universe of stars and galaxies on a very large scale, and quantum mechanics is the theory which describes the world of atoms, molecules and subatomic particles. These two theories work well in their regime, but when we try to combine these two theories, then problems arise. The two theories are inconsistent with each other, and it's been a long uncherished dream of many physicists to combine these two theories. There have been made many attempts to combine these theories since many years. Even on the deathbed, Albert Einstein tried to combine these two theories, but all the attempts made are not completely successful. Physicist Julian Barbour has suggested that the inconsistencies which arise in these two theories are because of the concept of time in these two theories. So if we remove time from these two theories, then we will be in a position to combine these two theories. So according to Julian Barbour, the main culprit is time. If we remove time from these two theories and consider that the universe is timeless, then we will be able to combine these two theories. So how this can be done? Let's see. Julian Barbour is a British physicist and independent researcher. He did his PhD in general relativity. He is famous for his thesis of timeless physics, that is, time is an illusion, and he wrote a book in the year 1999 with the name The End of Time, in which he presented his theory that time is an illusion. He said that many problems arise in different branches of physics because of the supposition of a physical quantity which is time. According to Julian Barbour, there is no evidence of past other than our memory, and there is no evidence of the future other than our belief in it. Change merely creates an illusion of time, with each individual moment existing in its own right, complete and whole, which he called nows. Barbour also said that motion is an illusion. It arises due to a fixed pattern of changes which he calls time capsules. In the Newtonian picture, time is independent of space, and in block universe theory and special relativity, we have seen that time has been treated as like a fourth dimension. But Julian denies both the theories. That is, time is even not absolute like in Newtonian physics, like time is elapsing, or he even denies that time is the fourth dimension. There is no fourth dimension like time. He said that the universe which we live in is a three-dimensional universe, and there is no existence of any fourth dimension. He said that time is not the fundamental quantity on which all the physical processes depend. The change in patterns or the positions of objects is not determined by time. Rather, time is derived from the changes happening in the three-dimensional universe. According to Isaac Newton, the whole universe existed in an invisible framework of absolute space. According to Isaac Newton, the whole universe existed in an invisible framework of absolute space, and time is like an invisible river flowing throughout the universe without respect to or without reference to anything. But for Huygens, it seemed that there is something wrong in the Newtonian theory of space and time. So he wrote a letter to his friend Leibniz, and both of them agreed with each other that there is some problem with the Mr. Newton's theory of space and time. Huygens said that we cannot define anything in such an absolute manner, which Isaac Newton said, we can only tell anything relative to anything else. And later in the 19th century, Ernst Mach, who was a great philosopher of science, said that it's beyond our powers to measure changes in things with time. Rather, time is an abstraction derived from the changes in things. Mach's principle is stated as local physical laws are determined by the large scale structure of the universe. This he illustrated in a very simple manner. Suppose that you are standing on an empty field and you are gazing the stars in the sky, and then you start spinning. Then you will find that the stars will also start spinning, that they will start rotating in the sky as you spin. Now you will also notice that your hands will go upward while you spin, and when you see the stars moving in a clockwise fashion, then your hands move upward. So he showed that the property of inertia inherited in a body is somehow related with the large scale structure of the universe. That is, the inertia in a body is determined by or is affected by the stars and every stuff in the universe. But according to Newton, the inertia of a body is determined by itself. So this is the basic difference in the theories. Mach principle is even not the basic idea. The basic idea was given in the 18th century by the philosopher George Berkeley. And influenced by George Berkeley, Mach stated the principle in his manner. So the actual idea was given by George Berkeley. So why this idea became so important? Because Albert Einstein derived his general theory of relativity from what we call he called equivalence principle. So equivalence principle, he credited the idea of equivalence principle to the Mach's principle. But later, when the theory evolved, he even abandoned the Mach's principle. He said that inertia is inherited in the geodesic equation of motion and not in the existence of matter elsewhere. In a similar manner, Julian Barbour said that time is not in itself a physical quantity, rather time is an abstraction which is derived from the changes, that is the actual content of or the existence of, that is the actual content of our universe. So our universe is the large scale structure which is determining the evolution of time. So time is an abstraction derived from the changes inherited in our universe. So he is using Mach's principle to somehow define a universe which is timeless. He said that time is derived from the changes occurring in the universe, and we cannot define time if there is no change occurring in the universe. The general relativity came in the year 1915, and after 10 years of that, quantum theory emerged, like around in 1925 it started. And Paul Dirac, who has his major contribution in developing the quantum field or the matrix theory of quantum field, matrix theory of quantum mechanics or the matrix mechanics, he tried to combine the two theories, the general relativity and quantum mechanics, and he found that there is some problem. He even found that there is some problem with the concept of time in these two theories. General theory of relativity is an extension of a special theory of relativity, which we will study later in our course. But for now, I am just giving a brief idea that in special relativity, we consider a block universe in which we have 3 dimensions of space and 1 dimension of time. When there is no mass present, then the space is flat. If you consider a 2-dimensional sheet of cloth, then it will be completely plain. So space-time is flat. But if there is some mass like Earth or Sun, then the space and the fabric of space and time, which Einstein calls space-time, this 4-dimensional space-time, in this 4-dimensional space-time, curvature is created due to the presence of mass, and in that curved space, a body cannot move in a straight line. A body or a mass will always follow a curved path. So it will go in this manner. But while in a flat space, a body will move in a straight line. So this was the theory presented by Albert Einstein, and it's called general relativity. So many people try to combine the two theories, quantum theory and general theory of relativity, and Dirac was even one of them, and he made a conclusion that it's the 3D space which is changing and not the 4-dimensional space. So he questioned the general relativistic 4-dimensional map of the universe. So what Dirac was proposing in his 1963 paper was that the curvature is not in the 4-dimensional space, rather it may be in a 3-dimensional space, and there is some problem with considering time as the 4th dimension, or the consideration of block universe may not be appropriate, and that's why we are facing problems in combining the two theories, quantum mechanics and general relativity. Other thing is that in general relativity, time is very much flexible in manner. There is no concept of simultaneity in general relativity. Two events can be simultaneous for one observer but not for other. While in Newtonian physics, time is absolute, and quantum mechanics somehow supposes the Newtonian picture of time. It does not treat time as the 4th dimension of a space-time. And in the year 1967, the Wheeler-DeWitt equation came, which describes the universe in a timeless fashion. That is, the concept of time disappears from the equations and the universe appears to be static. There is no trace of time in these equations, and time completely disappears from the theory. So this was an attempt to describe the universe without the concept of time. So Julian Barbour arrived on a conclusion that the notions of time in general relativity and quantum mechanics are completely different. So we will have to assume that time does not exist if we want to combine these two theories and present the complete picture. And to combine these two theories, it becomes essential that we assume the concept that there is no time at all. So, what is Julian Barbour's picture of time or a timeless picture of the universe? So, let's see this. So, everybody is aware with the theory of Big Bang. Now, to illustrate the Julian Barbour's theory, we will assume a universe consisting of only three particles. Like these are the three particles. And these three particles make a triangle. Now the lengths of the triangles are, name these particles as A, B and C. So this length is A1, this is B1 and this is C1. Now after some time, there may be some change and the positions of particles can change. So from here to here, the particles have changed their positions. Now this is the new position. This is A, this is B and C. So the new lengths between the particles are A2, this is B2 and B3. And forever these lengths are changing. So for a three particle universe, the configuration of the particles in a space will change. This space is three dimensional. We are not considering here the block universe, because in the theory we are assuming that there is no time which is elapsing and even there is no fourth dimension of time. Now these pictures or these snapshots are referred by Julian Barbour as potential nows or simply nows. So this is one now, this is the other now. So from one snapshot to another snapshot, the universe is changing, and time is something which is deriving from this change. If you put this triangle just above this, then you will find that they are not congruent to each other. There is some difference or some change, and that change and from that change time is derived. So consider a three-dimensional coordinate system. This is x-axis, this is y and this is z. This is some configuration space. Now we will represent the lengths of these triangles on the three axes. So consider that this length is A1. Now this is B1. Represent B1 length on, or the AC length on y-axis and the AB length on the z-axis. So this is AB length, which is C1. Now in this three-dimensional space, this will be represented by some coordinate. So let that coordinate be A1, B1 and C1. So this triangle is represented by some point in this three-dimensional space. Now this triangle will be represented by some other triangle. You are seeing that the length of the triangle is somewhat increased. So this point must be somewhat here. So from one configuration space configuration to the second configuration. This is our first configuration and this is the second configuration. So this point represents a triangle in one configuration, and in the second configuration this point represents the second configuration. So there may be infinite number of such configuration, so we can plot infinite number of such triangles. Now if you assume that there is one equilateral triangle in which all the sides are same, and this triangle becomes bigger and bigger, but the shape remains same, that is always remains an equilateral triangle, then at some moment this length will be equal to this length, and the same for the z-axis. All the three lengths will be same, and if we plot those points, then it will lie on a line. So if we will try to represent all sets of possible triangles by some points in this space, then it will look like a pyramidal structure in which the vertex of the pyramid, this is a trigonal pyramidal structure whose vertex will be at this point, and all possible triangles which are being represented by some point will lie either on the surface or inside of this structure. So consider that at some moment of time this point represents a triangle, and after some time there is a triangle which is here. It can be here or anywhere. So all the points lying in this space can be adjusted in this structure. Now consider that this is our first triangle. This point represents our first triangle, and this point is represented by this point. So from here to here, the system or the configuration has changed from one configuration to other. So this is your second configuration. So it may have changed with some, there may be some triangles in between these structures. Like there is a triangle, it changes its structure from this to this, and from this to that. It is regularly changing its configuration. So from going from 1 to 2, there may be many points from which the configuration or the system is evolving step by step, and every point represents snapshots or the nows, and this is what Julian Barbour refers as platonia. So this point represents a triangle, and so for every point it represents some triangle or some configuration of our three particle universe, and this point is called the alpha point, because here you will find that there is some configuration in which the sides of the triangle is 0, and this shows that Big Bang is inevitable. When we consider time to be a linear thing, that is, time is like an axis. In the Newtonian picture, time is like an axis. So it goes to infinity or the eternity, and it's coming from eternity. Now if you assume that universe has been created, then there are two possibilities. Suppose that at this moment of time the universe has been created, then there are two assumptions. Some assume that time, like Newton, even before the creation of universe, time existed, and like Stephen Hawking, who said that time has a beginning, it started with the Big Bang. So you have to assume that time has some beginning. But from the Julian theory, we are seeing that that Big Bang is inevitable. You cannot avoid Big Bang. Some say that there is no Big Bang. The theory of Big Bang is arrived from the observations made on the galaxies receding from us, that is the Doppler's effects on the galaxies. But here from the theory only you are getting that there must be some Big Bang from where this configuration has started, or this configuration will always come to an end, which is called the alpha point. So Big Bang is inevitable in the theory, but in a linear time theory, when you consider time to be a linear quantity, then you have to assume that there may be Big Bang, or the universe is that the universe existed from forever, that there is no beginning of universe always existed. So from a simple model of all the possible states of these triangles in a three-dimensional space, we are seeing that how without any supposition of time, we are showing that the Big Bang must exist. So in Julian Barbour's picture of the universe, of this three particle universe, what eternity looks like is that it is the schematic of all the possible configurations or the points in this three-dimensional space, put in a schematic manner. In the linear time model, which Newton follows, time is like a river which is flowing since even before the existence of the universe. So we have eternity at both the ends. But in this theory, you have the eternities at both the ends are not same. Here and any point on the edge, the two eternities are different, but when you consider linear time, the two eternities are completely same. So going forward in time or backward in times looks like same in the Newtonian theory. And the moment of creation is based on some assumption, while in this theory the moment of creation is inevitable. You cannot avoid the moment of creation because there must be some alpha point. Now one thing which is very remarkable, which you can find here, that in linear time theory the events are come in a sequential manner, that is, they have an order. After this moment of time t1 has elapsed, then t2 will come if time has some arrow. Now here there is no such ordering of time. This event can come after this configuration, not event. Suppose that this has gone like this and then it's coming like to this point. So there is no order in this space. So we can say that every now or the every moment is simultaneous with every moment. So it looks like the universe is static in nature, and it's the change from one configuration to other configuration, and which gives the illusion that there is some quantity which is time, which is passing. He gives a picture similar to quantum mechanics in which all the states can exist, and when you try to measure, then the state collapses in one of the configurations. So in the similar manner, in the timeless picture, there is the possibility of all sorts of configurations, but and these configurations occur simultaneously. So we have a probability of every possible state. So Julian says that the way we perceive the universe psychologically may be completely different from what it fundamentally or physically is. So according to him, there is no linear time scale in which events occur in an order. All the moments are equally occurring simultaneously, because there is no concept of time in his theory. So Julian concludes that the concept of time is a well-founded illusion, and what actually real or fundamental is in the universe is the three-dimensional configuration of the universe, and mutual consistencies of the records leads to the existence of past. These records may be like the geological data, like the stones which we recover after extraction from earth. They gives you some now of a moment in the creation of earth, and it gives you some information or the record. Despite some positive sides of the theory, the Julian theory has gained well-founded criticism from many physicists like Lee Smolin and Sean Carroll. So the theory is even not complete, but it may give some direction to the new coming physicists who want to go deeper, or who want to know a way to combine the two theories of quantum mechanics and GTR. So in the coming future, we may have some theory which is consistent with all the laws of physics. So we hope for such a theory in our lifetime. If you like our video, please like it, share the video and subscribe to our channel, and thanks for watching.